So hello everyone, thank you for being here for our second presentation of our group meeting. And today Sabrina will present about evidence of dark matter in the CMB. So can you go?
So hi everyone, today I'm going to present about evidence of dark matter in the CMB acoustic peaks. So this is a topic that is important to me to understand, so that's why I choose this topic today. So basically we know that the CMB is the cosmic microwave background, so we basically know that the CMB is one of the main observables that we have and that we use to suppose the existence of dark matter in this case. So we know that the CMB carries the imprint of the early universe. So this includes the presence of dark matter. And today I'm going to talk about a little about the CMB power spectrum. That is our key quantity to try to understand why we suppose the existence of dark matter so we're gonna see a graph that I will show here in the next slides. So basically the process is that we need to find a spherical Fourier transform. This is starting from the photon fluid temperature. So basically, we can do this for the temperature anisotropies of the CMB, and we can do to extract the powered spectrum. We can do an averaging of the 2L plus 1 orientation. This is for the angular momentum. For each value of an angular momentum, but this is for CMB. So basically, the interpretation of this is that we use the power spectrum to compare to predictions of the inflationary Big Bang. So with these informations, we can have informations about the contents of the universe, so about baryons, photons, and this includes too the presence of dark matter. So basically, we have the CMB peaks that are related to acoustic oscillations of the primordial plasma of photons and baryons in the early universe. So basically, the CMB peaks is about, it talks about the oscillations of this plasma. It is about compressions and, como é rarefação em inglês? So it talks about compressions and rarefactions of the plasma. So for this, we have here the graphic for the power spectrum. So how we can see here, we have different heights for the peaks, and we have different amplitude for the peaks too. And as L increases, the power spectrum is decreasing. So we call this silk damping. So the positions and the amplitude of the CMB peaks will depend respectively from the dark matter density and from the ratio between dark matter and the normal matter. So in this case, the relative amount of dark matter and this baryonic matter. So how I say the CMB peaks, they comes from these acoustic oscillations. And we know that the CMB peaks will fit with the lambda CDM model. That is our standard model for the cosmology, the concordance model for cosmology. And basically, this model says that we consider the universe as being flat, Euclidean universe. It is dominated by an non-baryonic and cold matter that we call dark matter. And the expansion of this universe can be explained by a constant cosmological. That is the lambda in this case. So CMB peaks will fit with this model. So this is important because we can estimate precisely the parameter density for the dark matter. So this parameter is about 0.26 or 27. That means that dark matter will represent about 26 or 27% of the content of energy and matter of the universe. So the first thing that we need to do to take some information of how dark matter it is present in the power spectrum, we need to consider a function that will talk about fluctuations, the fluctuations of the photon fluid. So we have this function here that will depend on the position and this direction vector here for a particle, and that will depend on the temperatures. So we have here fluctuations in temperatures that comes from anisotropies. So we need to do a Fourier transform on this function, and we can through this find this function here that basically will give us information about some espaço de ondas, wave space. So we have the evolution of this function through the Boltzmann evolution equation. So we have here the Newtonian potential here, and this tau here, it is a quantity that will depend on the cross-section of the scatter of the Thomson scattering. That is something that we have before recombination in this case. So, and this term here is about the velocity of the perturbations of the matter. So we can assume a solution that will depend on Legendre polynomials, and that will depend on this variable that it is an angular variable that will depend on the product of the k, of the k, and of the p. So basically we can find solutions for the angular momentum, that is this index here, the L, for 0 and for 1. So we can use these solutions, in fact, to try to understand how the perturbations of the photons was in the before the recombination. So this equation here is our monopole that will give us information about the density and homogeneity of the photons. And this is our dipole that will give information about the velocity of the photon fluid. So basically we have this regime here that is basically a regime where we are considering a strong coupling between the photons and the baryonic matter. So that's why we call this tightly coupled regime. So basically we can, I don't know how the author find these equations here, but we can find for this regime these equations for dark matter, baryons, and the photons. And we can see in the equation for baryons and the photons that we have here a term that is R that will link the the baryon density with the photon with the photon density. So and these terms don't appear here, but we have another term that is the potential that will appear here. And basically, we can take from these equations a link between baryons and photons. So basically, they are linked gravitationally and electromagnetically. So gravitationally, we have the potential phi and psi, and electromagnetically through the Thomson scattering. So basically, the electromagnetically link between photons and baryons will will, will be will be given by this term here that will link the baryon density and the photon density, and this tau that will depend on the cross sections of the Thomson scattering and the number of electrons. So we can find to conformal time two solutions to theta zero that it's a solution that is basically harmonic coupled harmonic oscillator. So this will depend on this K here, on this K here. And this K will depend on the density of matter. So basically, this if we plot this this function, this square of this function, we can find that the peak separation would depend on this baryon density. And if we add gravity in this case, we have like a shift in the graph for the oscillations. So we are adding here a potential that will add gravity. And for this potential, for this gravitational potential, we have the dark matter linked with this. So basically, these gravitational terms will control the relativity height of the peaks, the even and the odds. So, and this velocity here is for photon baryon fluid, and will depend on this air here that will link the density of baryons and photons. So basically, this is for before the recombination, and after the recombination, we have the free streaming. So we don't have more a lot of photons coupled with the electrons. And we have this before the recombination, but after we don't have this. So the photons can travel freely through the space. So we have photon perturbations that will not grow, and we have that the CMB can be basically a snapshot of this universe at the recombination. So it's like a photo, the CMB, after this process. So here I have the angular power spectrum that is basically our quantity that we observe in this case. We don't observe directly these functions here for the perturbation of the photon, but we can observe the angular power spectrum. So, and this will depend on the square of this function here. And we have the silk damping too, because we know that the peaks of the CMB will decrease as the L will increase. So we have this happening. And basically, we have for the presence of dark matter, showed by the second and the third peaks, and they can carry these informations about the presence of dark matter. So we have here a graphic that I take it from the material that I study. So for our model, lambda CDM model, we have this
Green.
okay. Era padrão, mas we have this green line here. So this is what we expected to see to fit with the observables that we have for the CMB power spectrum. And this is for the red is for if we just have baryonic matter. So this not fit with we observe, because if you compare what the graph that I show with this blue, it will fit almost perfectly, but not this red. That is a model that we consider just baryonic matter. And if we consider this model with dark matter, you can see that the third peak is more height. So for matter, you don't have this. So if you consider a model with dark matter and with baryonic matter, you can find a model that will be approximate with the lambda CDM model in this case. So
Well done.
So to start, I have a question. In your last slide, I didn't quite understand the other two possibilities. The dark matter to lambda and dark matter arrow curvature.
I don't understand
okay.
this dark matter curvature. I don't know what it's talking about.
So he's removing everything that goes to dark matter and putting in the term of the Friedman equation, which is coupled to the curvature. The same goes for the others. So replacing the whole abundance of dark matter put into dark energy, the whole abundance of dark matter put into baryonic matter. So the main message is, and there are other alternatives as well. Some of them try to convert dark matter along the history of the universe into dark energy. Some of them try to convert dark matter throughout the history of the universe into curvature, and slowly, by little, just into baryonic matter to say, look, there is no dark matter today, and all of them fail.
So when all these models replace dark matter with other things, they are all considering a flat universe.
I have a simple question. Can you show me a
graph
data where you talk about the baryon photons fluid? I guess
This one?
not. Yes. Did you say that the peaks on this spectrum is related of acoustic oscillation of the baryon photon fluid? What is the baryon photon fluid?
how what is it is a plasma.
It's a plasma?
Yes.
Yes.
A
But
hot
the plasma will have a temperature, of course.
yes.
How much is the low temperature? The high temperature?
No,
The plasma is dependent of the temperature.
the temperature is very high
Yes, but
of the
When you know in kelvins, how much is the temperature? You know what's the temperature of the CMB at the recombination? You know?
Remember we talked
Two
about
something.
2 points?
2.1? 2.1?
No, this is today.
Today.
Recommendation was higher.
Yeah. Yeah, you remember? 3,000 Kelvin.
And my question is, why you consider an angular moment? It's like this. The angular moment is the setup of the measuring of the spectrum
Or
or
this guy.
the sky.
Because it's not isotropic. So the fluctuation in the peaks
Yeah.
have everything to do with the mass, the accumulation, the baryon discrepancy spread across the sky, the universe. So you just map a 360-degree map, and you see the map. That patch is harder, that patch is colder, and this has everything to do how much baryons we have, how much less baryons we have. The interaction between baryons and photons determine how cold or how hot those matters components are.
What is favorite that collect this data is the
In the past, we had fetus, and then later we had WMAP 1, 2, 3, 4, 5, 6, 7, 8, and 9. Just one, but it's just accounting of 7 points, WMAP. No, before that we had one scope, COB, E, and then WMAP, and now we have Planck.
interesting
But we also we had another, it's like Atacama telescope
Atacama telescope.
and South Pole
I have
telescope.
heard that Atacama
So Atacama telescope and South Pole telescope.
Just this.
All of them measure CMB. And the main thing is, so we had Gold, Fetus, Planck, Atacama telescope, South Pole telescope, and all of them agree with each other. And so you see the error bar there? This is something she didn't mention. Is multiplied by 1,000. So we can see the error bar. By 1,000. Multiplied by 1,000. That's why, for instance, when you try to replace dark matter by anything else, you just cannot reproduce the data. So many of our colleagues who say, dark matter doesn't exist, and they work on modified gravity. And then I often ask them, so have you tried to fit the CMB data? Have you tried to fit the data? Our opinions don't matter, right? Have you tried to fit the data? No, the data, no.
Some of them say that there's a lot of parameters in the data. So you can have the analysis, and we are fitting with those parameters, but
Even if you try to fit with modified gravity, you cannot fit.
Yeah. This is an open question.
It's a closed question.
Close.
Closed problem.
we have one other astrophysical observation that gives the same value that the seeds of CMB provide to us.
So CMB in the end says that 27% of the overall budget of the universe should be dark matter. And other cosmological observations point to the same value.
Yeah.
Oh, a
I'm
question.
learning something.
But because I think I heard from someone telling me that this the data doesn't depend on the cosmological on the cosmology right?
Model.
Like, it doesn't depend on the longitude and yeah, or does it?
I
If
think
we
it
consider
does
other
depend because for instance, you're assuming that the universe had photons and baryons.
The data, I must like.
No, the data is always independent.
Okay. So like lambda CDM fit this data.
Yeah. So show again the next, the last, the before last plot. So this one in green is the theory. Is theory only. Now I'll go back to that other slide, Michelle. The one that we just this one. So this red one is not theory. The one is the curve that best fit the data. And that red curve lies exactly on top of the green one, Tisha.
Because I don't recall who, and I wouldn't say who, but I was saying that CMB was a pool of dark matter, and the person said, no, for lambda CDM, for this type of cosmology. And I got confused, like,
No,
if we consider other type of cosmology, the data will...
No, so I haven't seen any data, any theory that could replace dark matter within the CMB scope. There is one model that has been put in the literature, which is a model which does not have a cosmological
I
constant.
said CMB or lambda CDM?
Lambda CDM.
Oh, yeah.
So there is one model that does not have lambda, is not related to lambda CDM model. They don't believe, they do believe in dark matter, but they don't believe in the lambda.
Okay.
They want to replace the dark energy component, but it's one group, and that's it.
Yeah,
Just
So say, okay, we do need dark matter. So I heard a talk is Subisaka, is a well-known physicist on cosmology. He's a former professor of Oxford University, and now he's at Niels Bohr Institute. And he's an excellent speaker, so he knows how to convince people. He says, I feel in my bones. That's what I said. I feel in my bones that dark energy doesn't exist. So my life mission is to prove that dark energy doesn't exist. So his theory does fit one of the data, but not the CMB data. Some other ones, like the supernova data, is the same. To me, my opinion is that it's the same battle that we had with MON. MON does fit dark rotation curves, and that's it. So, okay, you don't get to pick which data you want. You have to pick the data that fits them all. That's it. Right? We are scientists, not philosophers. We have to reproduce the data, and that's it. There is no way around. In my theory, does not. We don't have to fall in love with a theory. If our theory does not reproduce the data, throw away. Get another one, or improve your own theory. That's fine. But many of the cosmologists, even in Brazil, they work on this, trying to. They invoke a coupling between dark energy and dark matter. There's a community in Brazil which was formed in this stuff, and it's Ricochetti and some others, which are not, let's say, it's still recording, right? So let's say it's not very popular, right? So it's not very popular, this theory anymore. Maybe in some days in the 90s they were at some point. Now not anymore, which tries to couple dark matter and energy. But it's fine. In the 90s, our data is the error bars were like this big. You could fit a cow. But now you have to multiply by 10,000 to see the error bars. So it's a completely different picture. So I have never seen something like this, like CMB. The error bars you have to multiply 10,000 to see the error bars. I've never seen something in nature like this. Never. Usually the error bars you see is that size and that. But you have to multiply by something to see. No, come on. It's like it's incredible. That's why these guys really deserve the Nobel Prize. It's amazing.
So let's
Okay.
take the speaker. Oh, see the chef in the meeting?
I think Zé ou Victor.
It was
They are. He was answering Manuel.
It's because you said that you didn't know where the equations came from, right? At some point in your presentation. You said, do you hear me?
Yes.
Yeah.
Yeah, at some point in your presentation, you said, you presented a set of equations. You said, I don't know how the auto got to these equations.
Yes. Yes.
Okay, so
It was
So
it's
answering.
just,
could you point her a reference which writes down explicitly all the steps to get these equations?
the only I know are the notes from my cosmology course. I can send it to her.
From David?
No, from Leo.
From whom?
They had cosmology with
Leo Medeiros.
Okay. All right.
I'll send it to her.
Thank you.
Did we thank us?
No,
Let's thank us.
Então, só os avisos, pode desligar. Os avisos é que próxima semana,
Thank you for
as
being
próximas 2 semanas eu não estarei aqui. Próxima semana